with the distributed lag model, you could do the same with x's. With the in the previous example with AR, we actually regressed YT on itself. Okay, but in many occasions, also x's or the other variables that affect y, it's better to include them. And in economics, we usually express equilibrium as a static form, in a static form, which is not necessarily the case. We always know that, okay, the price is set when quantity supply equal quantity demand. But this is not the case all the time. Sometimes you have surplus, sometimes you have shortage. So sometimes quantity supply is greater than quantity demanded, sometimes the other way around. But then this will be some sort of the equilibrium is not going to happen instantaneously, and there will be a sort of process of trial and error, and that will happen over time. So a very popular example here is the permanent income assumptions of Milton Friedman, when he said, okay, so if you think about this as current consumption, so your consumption this quarter will depend on your income this quarter and your income the previous quarter and the quarter before, and then going back. Okay, so basically your consumption or current consumption is a function of weighted average of quarterly income, not just this year, not this quarter, in the past as well. Okay, and that's why it's called permanent income. So people adjust to any changes in their income, so they adjust their consumption, okay, accordingly. So this is just an example, but this should tell you the idea here. So YT here depends on XT, so depends on X in time T in this quarter, and XT in the previous quarter. So what you spend today depends on your income today and your income the previous time period or the previous period, which could be, if your data is quarterly, so we'll talk about quarter, the previous quarter. If your data is weekly, so that means talk about last week. If your data is monthly, then we talk about last month. So the lag here means the last period, and that period would depend on the frequency of your data. Okay, so in this case, this is exactly the same model, so we're just trying to generalize the idea, not just talking about income, permanent income hypothesis. So in general, okay, how would we interpret these coefficients? Beta 0, beta 1, beta 2, up to beta q. So beta 0, which is attached to xt, so the independent variable in this time, in this period, in time t, that would be the short run or the immediate impact multiplier. Okay, so that means a change in mean value of the dependent variable following a unity change in your independent variable. So that's exactly the same interpretation that we would give to this beta here. So if this changed by 1 unit, how much this would change? But the difference now, we're talking about the short run or the immediate impact. If you sum these together, okay, that's called, well, the partial sums, called the intermediate multiplier. Okay, if you sum these all together to up to this one, that means you're talking about the long run or the total multiplier or the total effect. Okay, so don't be confused with the word multiplier, just the effect. Okay, so now I talk about this is the short run multiplier. I mean, this is the short run effect of a change in X today, how much it will affect Y today. Okay, that's the short run multiplier. So if you want to look at last period, t minus 1, t minus 2, blah blah blah, so then just add these together. that will give you the effect over the last, from the last 3 periods. Okay, and if you want to know the total or the long run effect, which we call here the multiplier, the long run effect, so just sum these betas together. Okay, but here the difference here, you see, YT with the distributed lag models, YT does not depend on YT minus 1, it depends on XT and XT minus 1. Okay, so this is different variable, not YT, not the same variable. With the ER process, so the variable is regressed on itself in the past. With the DL or the distributed lag model, so the X, you see XT, so X in time T and X in time T minus 1, and you could go back many lags as well. So this is just an example. And that, I think that was, yeah, that was unemployment and growth rate. Okay, so what I wanted to show you here, so this is the data, and I want to create the lag for unemployment. Obviously, the first observation, you lose the first observation because there's nothing before that. So nothing before 7.3, but the first lag here means this point. The first lag here means this point. The first lag here means this point, and so on. Okay, that means UT minus 1. You can think of G the same way. Okay, this is the change. So the change between here and here. So the difference between these two. The change is the difference between two. So this one is the difference between two. It's 0, didn't change. Okay, and so on. GL1, so again, this is the growth lag, the first lag. So the first lag means, should be this 1.4, 2, 1.4, 1.5, 0.9. Okay, so that just show you the structure, what we mean. So lag 2, that means you lose the first 2 observations, and then this is 1.4, you see this is 1.4. 2, this is 2. 1.4, 1.5, so that's lag 2. So when I say GT minus 2, I know what that means. Okay, so this is just how the data looks like. So here's the estimation. So what does this say? What does this estimation tell us? So we have unemployment rate, UT, our dependent variable, depends on G, lag 0 means GT this time. Okay, so the lag here is 0. Okay, there's an intercept. Okay, that's delta, or call it whatever you want. But there's here lag 0 means it's time T. Okay, lag 1, so means T minus 1. Lag 2, T minus 2. Lag 3, T minus 3. Okay, so let's look at the p-value. This one, the first in time T, it's significant. It's very small p-value. The second lag is significant. The third lag is significant at 5%. The third lag is not. Okay, but what does tell us? Again, it might be important to consider your x's or your independent variables in the past, their values in the past as well, with lag as well. Okay, so it's not just about yt minus 1 on yt minus 1. Also, xt could, again, xt minus 1 can have some impact on yt in this time period. And this is a very simple example that show you that unemployment rate in time t depends on unemployment rate, depends on growth rate in time t, and growth rate in time t minus 1, and in growth rate in time t minus 2. So 2 lags. Maybe the third lag is not significant, but at least we know that at least 2 lags are significant. Okay. So how would we estimate this again? So it's the same, the specification. How many lags to go back in time? So it's the same question. How many lags to go back in time with the AR process? There's more issues here with the x's itself, because if you go back many terms, So that means that can create multicollinearity between these x's, okay? Because do you remember when we said growth rate this year might be correlated with growth rate from this quarter, might be correlated with growth rate from the previous quarter. So that might create multicollinearity, and that was the main issue when we have the x's are linearly correlated, you remember? So that was one of the issues that we discussed the week before last week. Okay, so including these x's might create this sort of multicollinearity, or you may have a very small sample that you see every time we go back in time, we lose observations. So when you 3 lags, you're losing 3 observations, and also you need observations to estimate these parameters. Okay, so you might just have very few observations, or if you have very small sample, that might not be enough to do this estimation, or might not be enough to get a meaningful estimation. Or you could have not like this. This is a finite distributed lag, meaning that we had up to Q. So we know, like, we're going back 2 lags, 3 lags, 6 lags, 5 lags, but we could actually have something like this. This is like infinite distributed lag model where not defined how many lags. So what if we can convert this or transform this to something else, or somehow that we don't have really to worry about these number of lags. We don't have to worry about this large number of parameters to estimate. Okay, and this is the transformation, the Koyck transformation, that can actually, or actually does this. So what it does, assuming that these betas have the same coefficients and they decline as you go back in time, so that means the effect of this is on yt is smaller than this is smaller than this, and smaller than this, and so on. So you could actually convert this in that way. So if they have the same sign as we said, and they decline geometrically, so that means you could have the beta k, so the total, should be could be equal beta naught times lambda. Lambda here is a value between 0 and 1, and it's called the rate of decay. Okay, how much it goes, it becomes smaller every time. And 1 minus lambda in this case is called speed of adjustment. Okay, how fast or how quick the yt, your dependent variable, adjusts to changes in your independent variable. And in that case, the value of this beta k here depends on these two things, and on beta naught and lambda. Okay, so as we said, this value here, this lambda, will be between two values, 0 and 1. Okay, so if this is close to 0, so that means this declines slowly, so it's very slow. Okay, and that means the x values in distant past have some impact on yt. The other case, if this lambda is close to 0, so it's very small, so that means the impact of x in distant past have little impact on yt. So it depends on really on the value of these lambda. But what we know here is that, okay, so this 1 minus lambda is the speed of adjustment. The again, what do we mean by the speed of adjustment? Is that how fast y adjusts to changes in x. So if we talk about consumption and income in a time series context, or if we talk about the same example we give now when we talk about unemployment rate and growth rate, okay? So how fast unemployment rate adjusts to growth rate, or changes in or new levels in growth rates. So that's exactly that's what we said. So this should be smaller as you go back in time. And using this, we could actually transform this equation. Remember, that's the question I asked. If we have this sort of infinite number of parameters to estimate, if we can change this to this is exactly what the Koyck transformation does. It changed that to this model. See the difference between this model with infinite number of parameters to estimate into this model, which has only how many parameters to estimate here? 3. Okay, so in that case, we still have this is the speed of adjustment, we know that, and this is the, you know what this is again the immediate effect or the beta node, but this process now became AR process. You remember YT depends on YT minus 1 and XT. Okay, so infinite, rather than having infinite number of parameters to estimate, as is the case in this model, we have only another model where we can actually have only 3 parameters to estimate. Okay, so that's how we transform this distributed lag model, infinite distributed lag model, so where you can have a large number or infinite number, sorry, of lags in the X, or with the X, XT minus 1, XT minus 2, and then go back infinite number of lags. How to convert this, how to transform this into an AR process, and that will save you really having to deal with all these number of parameters, and reduce the number of parameters needs estimation into 3.